we are still using the Cornell plate. This time I'm using the diffraction grading. And the diffraction grading is just basically a whole lot of slits there. This particular one, I think there's 70. We'll double check that in just a second, 70 slits. And the more slits there are, actually, the closer the slits are together, the more pattern you have like that. Now, a big difference between the diffraction grading and the double slit is that the lights are much brighter. So that's one of the reasons why we are doing it. The math is the same for the multiple slits. Single slit, the math is different, but so I really do not need to turn the lights out for this one. So that is the middle spot right there. All right. Oh, there's more out here. And there's another dot right here going off the paper, but we don't need those. All right, so we'll turn off the lights briefly here. Let me pause this. All right, and then with the lights turned off, you can start to see the ones out here a little bit better and the ones out there better. However, we just need a bigger piece of paper if we were going to do it that way. So now let's go to the math and see what we get if we get a more accurate calculation for the wavelength. All right, so the vernier caliper is too small for dealing with this, so I pulled out a ruler and measured that the distance from end to end over the 9 segments is 25.9 centimeters. And so we can find the distance y for one of these by doing 25.9 divided by 9. All right, so y equals 2.87 repeating centimeters, or 0.0287 repeating meters. L is still the same as it was before. L is equal to 1.39 meters. I don't think it changed appreciably. And so now we are dealing with the formula right here. And so that is equal to, I think it's focusing on my hand there, is equal to D, which is 0.034, well, actually, that's coming from the Cornell plate, 0.034 millimeters. So if I want to put that in meters, 0.000 meters is D. So that's the value for D. Y is the distance from here to here, which we came out with is 2.87 centimeters. We can actually do that measurement to see if it makes sense, and it looks like it is about that. So 0.0287 repeating meters divided by L, which is 1.39 meters, times N, which is 1. And so we have that number right there divided by 100. All right, so that's in meters, then 0.000034. Oh, so that times 0.000034 divided by 1.39. And we end up with 7.04 times 10 to the negative 7th, or 704 nanometers. We are farther off than we were before, so what gives on that? Well, part of the problem is that we are now starting to get farther and farther out from this, and so our approximation over here, or the approximation here, starts to become a little less valid. So what I'm going to do is I'm going to pause this and bring out the other equation and do some calculations before I start the camera up again. All right, so now we're going to take a look at it slightly differently. We're going to use the less approximated formula, this one right here. Now the angle, if you recall, basically we have our source right here, we have what's straight across directly at it, and then we have, so this angle here is theta. This distance right here is y, and this is L. And so I know that the tangent of theta is equal to y over L. And y, if I come down here and I take my middle spot to the spot out here, that was 14.2 centimeters, so 0.142 meters over 1.39 meters. And from that, we got an angle of 5 point something, let's see. We got an angle of, I did an arctan here, 5.833 degrees. Now, in order to find the wavelength, I take the sine of that angle and multiply times d, and d I'm getting from here. That's the 0.034. So I did d times sine of theta to get the wavelength. And in this case, because is 1, 2, 3, 4, 5. So n is 5 in this particular case. So what I'm going to do is I'm going to take the tangent of that angle right there. Sorry, take the sine of that angle right there, multiply times d, which is 0.034 millimeters, or 0.000034 meters, and then divide by 5. And what I ended up getting was this answer right here, 691 nanometers. It's still above the range of what we were looking at before, so it's quite possible that I was a little bit imprecise in some of my measurements. But again, they are claiming that the range is 635 to 670 nanometers. And we got 690. We got slightly accurate last time, but you know, it's physics, and ultimately, that's the way it is.